Hello all, and welcome to our section on referring parameters for the transformer. So this is just another example of how we can make mathematical simplifications to the model. Obviously, as you'll see, what we are doing cannot be done in practice. It is just a mathematical technique. So by the end of this session, you should be able to refer parameters from one side of the transformer to the other, and you should be able to calculate input and output voltages and currents by referring parameters to either side of the equivalent circuit. So what do we mean when we say referring parameters? Currently, when we look at the equivalent circuit, it looks something like this. We have the primary and the core losses, and then we pass through an ideal transformer, and then we have the secondary losses, and your terminals are connected on these sides. What we do when we refer the parameters is we take the losses from one side and we put it on the other side. So we can either take the secondary and put it on the primary, or we take the primary and put it on the secondary. So when we do that, we have all the losses on one side and then the ideal transformer. Or alternatively, we could have the ideal transformer first and then we could have the losses on the other side. So either way, we would have all the losses lumped together and the ideal transformer separately. So to do this now, since we are changing the impedances, we're taking them from one side and putting them on the other side, the thing that is going to change here is the current through those impedances. Now, what we have to do is we have to make sure that the power that the impedance dissipates is the same regardless of the side that it is on. Now we know power is equal to I squared Z. But since the current on each side of the transformer differs, this means if we simply transplant the impedance with the value from the secondary side, for example, and put it on the primary side, that we're going to have a different power dissipation in the component. So what we need to do is we need to adjust the impedance so that it gives the same power dissipation as it would if it was on the correct side of the transformer. So we know I1N1 is equal to I2N2, so that I2 is equal to N1 on N2 by I1. Now if we have on the secondary side a component Z, then the power dissipation there would be I2 squared Z. And we could substitute then this for I1, and we will get N1 on N2 by I1 squared Z. So this is the power dissipation of the component in terms of I1. Now if we treat I1 as the current, we will see in order to get this, if I take it out here, that I need to scale the impedance by N1 on N2 squared to give me the same power dissipation. I can't scale the currents because remember the currents are fixed for those parts of the circuit. So what I do is when I shift the impedance, I'm going to change it by N1 on N2. This is from secondary, which is side 2, to side 1. I'm going to scale it by N1 on N2 squared. So whatever that Z is, I just simply multiply it by that number, and then that will give me on the primary side the same power dissipation as I would get on the secondary side. So when I bring that to the primary side, I will have R equivalent, which is R1, the primary side resistance, plus R2 multiplied by N1 on N2 squared. And similarly, X equivalent is X1, which is the primary side, plus X2, which is the value on the secondary side multiplied by N1 on N2 squared. Now, although we call these things losses, remember as we said in the previous video, only R really counts as the losses because this is the only place power is dissipated. The leakage parameters and the inductances contribute to voltage drops, and so that means not all the energy makes it to the secondary side, but the power is not strictly speaking lost. It just goes into the fields and then comes back out. So remember, when we're going from one side to the next, say we're going from the secondary side to the primary side, which is what we would commonly do, then we go n1 on n2 squared. And if we're going from the primary side to the secondary side, it will be n2 on n1 squared. So note that the numerator is the side that we're going to, which is the same thing we do with voltage, except if we're going from voltage here, V1, then V2 is equal to N2 on N1 V1. So the impedance is the same, except for the impedance, this is squared. But just like voltage, the side you're going to will be the side that is on the numerator. So let's talk now about efficiency. And you all know that efficiency is basically the output power over the input power multiplied by 100 if you want to get it as a percentage. And we could write this in a few different ways. We could say the output power is actually the input power minus the losses, or we could say the input power is really output power plus losses. So all of these things are different ways we could write the same equation. The important thing to remember, however, is that only the R's, not the X's, contribute to the power loss. Now here we have the output power V2I2 cos theta load, and this is very important. What we're looking at here, since it is the output power, remember we have the transformer, and I'm just drawing the ideal transformer here. In reality, you'd have all the losses. The V and I here, V2, I2, cosine theta 2, or theta load, which is the power factor at the output terminals. So this is the output power plus losses. And again, remember, here it is just the resistances, not the reactances that we use. And these currents, I0 and I1, they correspond to the currents flowing through these resistances. If we go back till we get the circuit, I have to go back a little way, you will see I0, R0, and I1 by R equivalent. So one of the common mistakes is using I in instead of I1 or I0. So all you have to remember is this is just the power dissipation in that component. So the same way you'd have done it in circuit analysis is the exact same concept here. So we could also write it, if we wanted to do it in terms of input power, and I had V1, I1, I could say the input power is V1, I1 cosine theta in, and that would be the power factor at the input. So this is also something to be wary of. Make sure when you're finding the power that the power factor corresponds to the position in the circuit that you're looking at. This is a very common mistake. Sometimes people use the power factor for the output at the input, or the power factor for the input at the output. So make sure that you use the power factor for the correct terminals with the corresponding voltages and currents for those terminals. So the last thing is voltage regulation. And here voltage regulation, V no load minus V full load on V full load multiplied by 100. The no load voltage refers to the open circuit output voltage, and this gives you the condition which is minimum voltage drop, because you have the least current. So the least current flowing would be the least voltage dropping across the components, so you would get the voltage which is closest to the nameplate voltage. And then for V full load, this is when you'll have the maximum voltage drop. The maximum voltage drop that the device is rated to handle. So what you want for good regulation is essentially you want V full load to be close to V no load, and that would give you a very small percentage regulation. So the smaller the better. What it means is if V full load is close to V no load, it means that if the transformer is, say, we have a 6600 to 230 volt transformer, the no load voltage, if I apply 6600 volts on the primary, I should expect to get 230 volts on the secondary. But as I increase the current because of the series losses, I would notice that this is going down. But if I have very good regulation, it won't go down that much, and I would still get, even with a full load current, I will still get close to 230 volts. So that is for a very good case. So that means the regulation is very small. If the regulation is large, it means that you have a large deviation between the no load and full load conditions, and that's not something you want, because in power transmission you want to ensure that even when you have a lot of load on the system, the voltage remains at the stipulated levels. Remember, you need the proper voltages for your devices to work on, so on and so on, in your homes and at industries. So let's look now at an example. We have a pole mounted single phase 100 kVA 6600 to 230 volt distribution transformer, and it has the following characteristics. R1, which is the primary side loss winding resistance, 1.56 ohms. The secondary side, 0.005 ohms. So you could immediately tell here which side is the high and low voltage. Remember, the higher voltage side would be carrying a lower current and therefore would need a thinner winding, and a thinner winding would have a lower cross-sectional area and so a higher resistance. The lower voltage side would have a higher current, which would require a thicker winding and therefore would need a thicker conductor, which would carry a larger cross-sectional area and therefore have a lower resistance. So all these are little checks you could make to ensure that the question makes sense. And then we have a leakage reactance of 4.66 ohms on the primary and 0.016 ohms on the secondary. And the three questions you're required to answer are: find R1 XM given the no load current of 0.251 minus J 0.968. For a full load current of 0.8 PF lag, find the secondary voltage and voltage regulation, and find the efficiency of the transformer. So, and this of course would be the efficiency of the transformer at full load. That is implied there. So let's start off by finding the values of R0 and XM. So the first thing we're going to do is draw the magnetization branch. So we know the voltage across this is V1, and we know the currents. The currents were 0.251 and minus J 0.968. So we have 0.251 minus J 0.968. Let's see. Yes, 0.968. And we know they split like this because we have the voltage here over a resistance that would give us the real part of the current, and the same voltage over the reactance would give us the imaginary part of the current. This is only true because the resistor and inductor are in parallel. If they were in series and the voltage were across both of them, then we couldn't say the real current is through the resistor alone and the imaginary current is through the inductor alone, because it's the same current through both of them and the voltage drops across both of them. In this case, however, they are in parallel, so the same voltage is seen by both. So we know that R0 is V1 on I0, so we could calculate immediately. This is 6600 over 0.251, and that would give us 26.3 kilo ohms. And similarly, 6600 over 0.968 would give us 6.82 kilo ohms. And that's it. That's all we have to do to get R0 and XM. And this is similar to what you do in your labs also when you're identifying the parameters. Good. Now, so for the next part, part B, we have to find the secondary voltage and voltage regulation. So what I'm going to start by doing is computing my equivalent circuit by getting R equivalent and X equivalent. So I'm going to refer the parameters to one side of the transformer. Of course, here I will have the ideal transformer here. I've just left that out because I only want to focus here on the loss circuit. So I know R1, R2, X1 and X2, and what I need to get is the turns ratio. So the turns ratio is 6600 on 230. So remember, 6600 is the primary, 230 is the secondary. I'm going to go from the secondary to the primary, from N2 to N1. So N1 goes on the numerator, and my ratio there is 28.7. So if I take the parameters, so I get R equivalent, which is R1 plus 28.7 squared. Remember, this is N1 on N2 squared by R2, 0.05. I should get 5.68. And similarly, X1, 4.66 plus 28.7 squared by 0.016, I should get 17.84. So that gives me the equivalent R of 5.68 and J 17.84 as my loss, my leakage inductance. And now I have R0, XM, R equivalent and X equivalent, and I could go ahead in finding what V2 is. Remember, I need to find the secondary voltage. This V2 is not the secondary voltage, it is actually the voltage at the primary of the ideal transformer. But once I find V2, I just have to use my turns ratio to get what the voltage on the other side is, and that would be my final answer. So the first thing I'm going to do, I need to find, I know V1 here, I need to find what is the voltage drop across here to get V2. So what are these currents? I need to find out those currents in order to tell me what the voltage drop is. So I know S is equal to VI conjugate, and S is 100 kVA, and the power factor is 0.8. So I could compute using I is equal to S on V, I conjugate is equal to S on V. I could compute what the value of IN is, because I know S and I know V is 6600. So that gives me IN at 15.15 angle minus 36.7. That is this current here. I also know I no load because this was given in the question. So I could work out I1 is equal to IN minus I no load, and this was I no load here that was supplied in the question. So I could work out I1 as 11.869 minus 8.122J, which is 14.38 angle minus 34.8. Now that I know this current, I could work out this voltage drop by simply multiplying I1 multiplied by Z equivalent, and that is what I have here. So V2 is V1 minus this voltage, and I end up with 6389.8 angle minus 1.49. Next, I want to find the output voltage. So I simply multiply that answer by the turns ratio. I'm going to the 230 volt side, so that gives me 222.68 angle minus 1.49 volts. And that is the end of this part of the question. You could see here it is very similar to what we would have done in circuit analysis. We are just finding voltages and currents. So just like AC circuit analysis questions, this is what we are doing. It's the same theory. All we have to do now is apply it to a very specific circuit topology, which is the equivalent circuit for the transformer, but all the same theory holds. And now we need to calculate the voltage regulation. So we know the regulation is given by V no load minus V full load on V full load. In some texts you would see V no load here, but we opt for V full load. And that would be 230 minus 222, and I'll just go back here. This is the 222 you got here, 222.68. You only need this magnitude part. You don't need the angle for that part to calculate the regulation. So 230 minus 222, this should be 222.68, but just for simplicity I left out the 0.68, and you get 3.6%. And last, we want to find the efficiency, which is P out on P in, and that is the same as P in minus P losses on P in. The losses I0 squared by R0 and I1 squared by R equivalent, and we have I0, which was supplied in the question. We worked out R0, we worked out R equivalent, we worked out I1. So we remember for the losses, these are all the magnitudes here that we need. The angles don't come into play when you look at the power losses. So that gives us 2831.8 watts, and the input power is simply the apparent power multiplied by the power factor. If you remember your triangle theta Q S, then P is equal to S cosine theta, which is equal to S by the power factor. So that gives us 80,000 watts, and then we could simply plug it into our equation, 80,000 minus 2831 on 80,000, and we get 96.5%. So this is a question I'm going to pose to you now. How would this solution change if the magnetizing branch was not shifted to the input terminal side of the circuit? And I think you could go and work this out and see what is the difference in the solution. So remember, when we originally looked at the loss circuit, the magnetization branch was here. And we said for simplicity we are going to move it to this side. But what happens if we didn't do it? What happens if we left it on this side and took it off from here? So that's what I want you to look at. What would be the difference in the results? And then you could see whether it is a good, whether it works as a simplification or not. So in summary, by now you should be able to refer parameters from one side of the transformer to the other. Remember here, you just use the turns ratio squared, with the numerator being the side that you're going to. And the other thing you should be able to do is calculate input and output voltages and currents by referring the parameters to either side of the equivalent circuit. And remember here, it's just like your AC circuit analysis. The same theory applies. It is just a different circuit, a fixed topology circuit that we're working with, which means it should be even simpler. So that brings us to the end. Next time we will deal with three-phase transformer configurations.